Follow Shadow Junior Twin.
So, part two of our long journey of covering all of A-level computer science before paper one. Now we have 137 days left, and we're only on our second video, but that's loads of time. We're getting through it. We're actually on schedule, and today we're going over stacks and queues. Very nice topic. And the reason why I call these intuitive data structures is not because I think they're easy. I know different people find different things difficult. Tongue twister right there. But the reason why I call it intuitive is because we come across these in everyday life, right? And the two examples that I'm going to repeatedly recall throughout this presentation is a stack of Oreos, and this can be a stack of anything. I just like Oreos, and they're quite easy to stack, probably only behind Jenga blocks. And then we'll recall a queue for a concert. And a queue is just anything which has a rear and a front. So you could have a queue in the canteen, a queue for a restaurant, a queue at a start, like a queue for anything. But these are the two that I'm going to refer to. So let's go over the definition of a stack. So a stack is an abstract data type with a last in, first out structure. And what's a last in, first out structure even mean? I mean, you can read this, but I feel like it makes more sense if I just talk through it. So if I want to add an Oreo to my stack, it has to go on the top. I can't add it in the middle because how am I going to do that? That's not how it works. That's not how it works. Let me make a cute little Oreo. So I have to add to the top of a stack. But if I then want to remove an item from the stack, I can't remove this item because I'd have to remove this item, this item, this item, this item, this item first before I can remove this one. So whatever's at the top is the first thing to be removed. So whatever was last added is the first to be removed from the data structure. And that's what last in, first out actually means. And that's pretty much it. I mean, you might need to understand why you want to use a stack in a scenario because you might think, why is last in, first out required? But apart from that, you just need to understand conceptually how to implement the things you need to do with a stack. And those are three things. You need to know how to push to a stack, which is adding to it, pop from a stack, removing an item, and peeking, which is just, you're not removing an item, you're just looking into it and seeing, okay, this is the top item. I'm not removing it, I just want to see what it is. So let's go over how to push to a stack. And we're going to talk about things called pointers, right? And a pointer is just a variable that points to the memory address of your data rather than data itself. So it's pointing to the index of the data, not what the actual data is, right? So for example, let me make sure this is proper solidified. If we have an array here and it's containing A and B, the pointer for the front of the array would point to index 0. It's not storing the value A, it's storing index 0. So you could then go array pointer and it would recall A. So let's actually implement it. So we create a global stack. The reason why I've used global variables is because we want it to be updated within the function. Don't really worry about that. That's not really what I'm trying to get across here. I'm trying to get across how you can implement these in pseudocode. That's the main idea. So we have a stack which is empty with a max size of 10, nice and easy. And then we have a global top pointer and we set it to -1. Why do we set it to -1 instead of 0? Well, that's because we're going to increment it by 1 before we actually add data to it. And the reason why we set it to -1 is we're going to think about that more when we're trying to pop items. But anyways, let's actually look at our function. So we pass in stack, we pass in top pointer, we pass in data. We don't actually have to pass in stack and top pointer because we set them to be global variables. But we're going to go over global and local variables later on, so don't really worry about this right now. This is just pseudocode nonsense. Anyways, we need to check if the stack is full. Well, how do we check if the stack is full? We have our max size to be 10, so if top pointer is equal to max size -1, because remember, indexes start with 0, and then 1, and then 2, oh, whoopsie, and then 3, and so on and so forth. So if top pointer is equal to max size -1, the stack is full. We can't add anything to it because the stack is full, we have to return false. However, if this isn't the case, we can then increment top pointer and we can add the data to the location, the pointer location within the stack. So let's actually get a little drawing going on. So we have A, B, and we have a free slot up here, index 0, index 1, index 2. Top pointer is going to point to here because this is the top of our stack. This is what's at the very, very top of our stack. So we're checking if top pointer is equal to max size -1. In this case, max size is 3 because this queue only has 3 things within it. Only has 3 slots. Is top pointer equal to max size -1? Is 1 equal to 2? No, we move on. We then increment top pointer. So top pointer is now pointing here. And we add the data. And let's say the data was C, right? We're adding C to top of the stack. Nice and simple. So how does a pop function work? So let's see, how do you think you check if we can actually pop an item from a stack? Well, for push, we checked if the stack is full. So for pop, we have to check if the stack is empty. How do we do that? Well, we initialized it to be -1 earlier. Remember we mentioned that? So now we need to check if top pointer is equal to -1. Typo right here, great. And if it is, then we have to return false. We can't remove anything from an empty array. That's not an empty stack. We can't do that. But if we get past this selection, we can then set whatever the top of the stack is, the data, and decrement top pointer, right? We want to remove it down. We want to move it down 1. So the top pointer is now pointing to the item below that. And then we return data, return whatever we just created. But if you actually think about how that works, top pointer was pointing here. We then decrement it down to here. We're not actually removing B from our memory. It is still in our memory location wherever our stack is held within our computer, but we're just changing the pointer. And that's the whole point. That's a nice pun right there. We're changing the pointer. We're not actually changing the memory location of data. The pointer indicates what's at the top and what's at the bottom, right? The peek function. The peek function is very simple if you know how to pop, because it is the exact same, but we're not going to be decrementing the top pointer, right? We only want to see what's at the top of the stack. We don't want to change what the top of the stack is. So I'm just going to flash this on the screen. It's the exact same as if we do not decrement top pointer. Perfect. So that's stacks. It's a very, very nice and very simple. You only have to keep track of one variable, which is top pointer. But queues, you can't just do that, right? Because since stacks have a last in, first out structure, you only need to keep track of one pointer. But queues, let's see if you can figure this out. What kind of structure do they have? Well, they have a first in, first out structure. Whatever was added first to the queue, if you're the front of the queue, you're the first to leave it. You're the first to get out, right? Which means that we have to keep track of 2 variables. A front variable that keeps track of the index at the front of the list, and a rear variable, sorry, not the list, the queue, and a rear variable that keeps track of the next available index in the queue. So if we have a queue here, we have A, B, and we have a gap right here. The front index is going to point here, so 0, 1, 2, and our rear index is going to point here, the next available free slot. It doesn't point here, it points here. So what things do we need to know how to do to a queue? We need to know how to add to a queue and remove from a queue. So very simple. We need to know how to on-queue and de-queue. That's the terminology we use. So how do we on-queue? So we're going to talk about on-queuing in a linear data structure, the linear version of a queue, but a queue could also be circular. And we're going to talk about that later on, but let's first go over the easier linear implementation. You might actually see why we need circular queues as we talk about linear queues. And if you do, pat yourself on the back because you can spot it and you can figure it out because you're a smarty pants. Anyways, how do we on queue? So we set an empty queue as an array. We have a max size 10, same as a stack, just for simplicity reasons. We have 2 variables, right? The front pointer and the rear pointer. Ooh, misspelling right here, love to see it. And when we add to a queue, we have to do the same check as a stack. We need to check if it is full. How do we do that? Same thing as a stack too. We're checking if the rear pointer is equal to max size. Now this is slightly different, so get this in your head. Let's speed run back. Here, we did top pointer is equivalent to max size -1. Now we're doing not -1, there's no -1. Well, why? That's because rear points to the next available slot in the queue. It doesn't point to whatever the back of the queue is. It's pointing to the slot after the back because it's pointing to the next available slot. Make sense? Okay, nice. If you get that in your head, then the rest is kind of easy, right? We're adding to the queue whatever data was to the rear index because it's pointing to the next available free slot, and we then increment rear. Since this slot now contains data, it's not the next available free slot anymore. We need to add 1 to it and move on to the next slot. So that's on queue. And de-queue is kind of simple, but it's different to how we check if the queue is empty in a stack. Let's go back. In a stack, we just have to check if the top point is equal to -1, right? And that means it's empty. But in a queue, we have to check if the front is equal to the rear. remember how we initialized the queue? We had you can see the initialization up here. Front and rear are both set to 0. That's because the next available free slot is index 0, and the front is also index 0. So if we check the front and rear to be the same in a linear queue, that means the queue is empty, right? If we add A, the rear then goes over here. And if we add B, the rear then goes over here, so on and so forth. If we remove A, the front's now here. If we remove B, the front's now here. So the queue's empty, right? There's nothing in it. Hopefully that makes sense. And then this part, again, kind of simple. Once you understand this part, you just you set item to queue front, you increment front, and you return the item. Because now the front index has removed the item it's been removed from the queue. Yes, it isn't removed from memory, but it's been removed from the queue because the front index is now past it. But now we're starting to see issues, right? With a stack, it's okay. We don't run into this issue because of how a stack works. But with a queue, let's look at this right here. If we add A, B, and C, this is a full queue, right? Rear is going to be pointing to this imaginary slot over here because it's full. So it's pointing to the next available free slot, which is nothing. If we remove A, this slot's now free, but rear can't circle back round. Get it? Circular. It can't circle back round. It's pointing to this slot here, which is a bit of a problem because now we're wasting memory space, which we do not want to do. So how do we fix this? How do we deal with this issue? We do something called modular arithmetic, which is a bit of a spoiler. But we want the front and rear to circle back around to index 0 once it reaches the max index, which in this case is 7 because the queue has a size of 8. So how do we do that? Modular arithmetic, spoiled. So if the max size of the queue is 10 and the rear pointer reaches index 9, we need to loop back to index 0. So what can we do? If rear index is currently 9, this is how we can update it. 9 add 1 is 10, and 10 modulo 10, if max size is 10, is equivalent to 0, because 10 divided by 10 equals 1, remainder 0. The remainder component is 0, so that's why we get this result. So how does onQueue work now? So once you understand that in your brain, it's actually not too complicated to implement. It's quite similar to a linear queue. So we have the exact same things as earlier, but now our check is different, right? We need to increment rear, do that modulo max size and see if that's equal to front. Then that indicates that the queue is full. And then we increment rear, just how we mentioned before, right? We add 1 to rear and then we do modulo max size. Because if it was 9, it would increment to 10, then we do 10 modulo 10, background to 0. So it's circling background. I'm just going to flash this on screen, then we'll move on to DQ. Now this is very similar to DQ of linear queue, and then again, need to change front. That's pretty much the only thing. That's the only thing that's changed, hasn't it? Front is now changed like this. We're doing front add 1 modulo max size, because this then allows it to loop back to index 0 once it reaches the max. Hopefully that makes sense. So, priority queues. Priority queues are something you need to understand, and you need to understand how they work, but you don't need to actually know how to implement them. It's quite complicated it's quite complicated to implement. I'm going to talk about how you could implement it, because it technically could come up, but you wouldn't have to do it from scratch. You could technically need to know how to do the other things from scratch, although it's very unlikely to be asked how to do that. So, what is a priority queue? So before I put any words up on the screen, I want you to think of any queue that you'd see in real life. The queue that I like to go to an example, let's go to the concert example. If you have a concert ticket, which is VIP, because we're rich, and I've got a standard ticket, so I'm waiting with all the normies, you can then walk past me, skip right through, and walk straight in because you have early access. You have priority over me. You can skip people that have lower priority than you, right? So a priority queue essentially means that items with a higher priority are placed in front of items that have a lower priority to them, right? If you buy a ticket to a concert, you can skip the line and enter with early access, just as I said. So this actually isn't too bad to implement. You just have to think about many things at once, because you have to implement the regular onQueue and DQ, and maybe you have to do it in a circular queue manner, and then you also have to do priority too. It's just too many steps to be asked in a past paper. But this can be done by just searching through the queue until you find the correct location. You can just use a linear search, right? because you need to reach a point where the data behind you has a lower priority than you, but the data in front of you has a higher or equal priority to you. If it has an equal priority, why are you going in front of it? You can't. So that's the kind of condition you're looking for. Okay, exam questions. Let's take a trip to GoodNotes and go over some exam questions. So let's give this a read together. And then we're going to go over the mark scheme, the official mark scheme, to see if we're right. Sorry, I've just realized I've been blocking your view the whole time. So basically, once you read this, you realize that we're just being asked to describe how pop works. So, pop, stack, as you can see here. What do we need to do? What do we need to check for? Well, if we're checking pop, we need to check if it's empty. That's going to be our first mark, right? We're going to check if stack is empty. And then what do we need to do if it's empty? I don't know. If so, return null slash, I don't know, -1 / false. Just return something that indicates that this function has not gone ahead because it's empty. And then otherwise, what we need to do, we need to return data at top pointer. We need to comment top pointer. For these describe questions, you're able to write bullet points, right? For explain questions, you can't, but for describe, you actually can. Let's go look at the mark scheme. So we want to check the stack is empty. So we get our first mark. Nice. And if so, return super value. Nice. -1, null, do nothing, give warning. I don't know, return false. All of that is okay. If not, decrement top stack, return the value in element top stack from the array numbers. Nicely done. So we would get all 4 marks here, right? Which is lovely. So let's go over to the next question. And this is a common question you'll get if you're asked to actually program something. We'll get given a skeleton and we've got to fill in the gaps for marks. The function push inserts its parameter data value. Well, that's just a free mark, right? If you know what a parameter is, that's just a free mark. You're told that it's a parameter in the function, so just write it there. Perfect. And updates the appropriate pointers. Complete the function push using pseudocode or program code. So, remember, when we check push, we need to check if the stack is full, right? So, how do we check if something's full? We need to check if the top pointer is equal to max size, right? But here we're doing, if it doesn't equal max size, then you actually continue on with the thing, right? And we're told, if you go back to the beginning, it's 100 elements, right? So we know that this is the case. And actually, we need to change our answer here, because remember, we're told that top stack stores the index to the next free space, not top pointer. Read the question, people. So let's change this to top stack. And then whenever we're inserting something into the array, you don't even have to read what's going on. We know we're going to have to use the pointer that we have established. And then remember, if we're pushing to an item, we're pushing to the next available free slot. So since we've added an item to that slot, we need to increment it, right? There's already a plus here. Let's remove that and just write 1. We're incrementing it because the next free slot is now the next available slot. That makes no sense, but the next slot is now the next available slot. Let's go to the mark scheme. We have data value, top stack 1. Data value, top stack 1. So nice. Then again, we get all 4 marks. These are kind of give me's. If you're able to do what I went through early on in this video, then these are just give me marks, aren't they? So, write an algorithm using pseudocode programs, call the function push. So we know we need to call this some point with the value 15. Remember, we add the parameter data value. So that's what we're going to push into it. And that's the parameter we're going to add to it. Output a message saying added if the value was successfully inserted, and output not added if it was full. Well, it returns false if it's full and returns true if it was added, right? So this is actually quite a simple question, and this is a total of what, like 12 marks. This is really nice. Added equals push 15 if added equals true. Then print added. Else then print and if. Nice question. Let's go down here. Added equals push, if added equals false, print not added, else print added. So you can see we would get all the marks here. This is pretty much what we did here, isn't it? So now let's go on to cues and how cues work and some cues exam questions. So state the purpose of head pointer and tail pointer. So we went over this earlier. It's head pointer points to the what? To the first element in the cue. And then tail pointer points to the next available free slot. Instead of slot, let's say free index. Sorry, my handwriting's a bit chopped. I'm writing on a I don't know, like a pad, I guess. So on cue will add data to the queue. DQ will remove data from the queue. Show the contents of the queue and the position of the both pointers after the following actions have been executed on the queue shown in figure 4. So this figure right here. So what happens is we have, so let's add it, 20, 15, 3, 2. 20, 15, 3, 2. And these order of operations is very, very, very important. First of all, let's go back to check the mark scheme. Here the difference by the first element in the queue to identify the next free space in the queue, next free index. Same. In fact, free index is a ball better than free space. So we get both of those marked there. Lovely jubbly. And then let's finish this question. So we on queue 20. So we're gonna add our pointers are at the end, but let's just finish the question first. So then DQ, so remove 20 here and remove 15 here. So this is where front is pointing. And this is where rear is pointing. These are just give me marks. Once you know how it works, just give me marks, isn't it? So look at that, lovely. Another 2 marks. Now let's look at part C. A queue is used to store ID numbers of jobs that a program needs to process. Some jobs will be given a priority, so boom, buzzwords, priority queue, which means they need to be processed first. Spelling this queue is not a suitable data structure for this algorithm. So the queue spelling is first in, first out. You can write FIFO. So you can't add items to the middle of the queue. Only the rear of the queue, right? Good spelling. So a queue is a FIFO structure. That's first mark. The queue will not allow new data inserted at the front, only allows new data to be enqueued at the rear. See, these are just give me marks. Once you understand how all this stuff works, these marks are just give me's. Let's go back over here. So, you can also be asked to write a couple long form questions relating to stacks and queues. And this may be asking why you would implement a stack/queue in procedural programming or OOP, so object-oriented programming. But this is more of a test of your knowledge surrounding procedural versus OOP. And this is something we will cover because it's quite a big part of paper 2. There's not actually any explicit OOP we need to cover, but I'm going to go over a bunch of programming questions and just what could come up. And that will be a lot of OOP, but we'll talk about that another day. And then you could also be asked how you would use a stack queue in a given scenario. And this is where you would recall stack is last in, first out, queue is first in, first out. Why is that useful? Why does that mean we should use it in these given scenarios, right? Remember, queues can allow for priority, but in the exam question we just did, it shows that sometimes certain implementations of queues means you can't do priority. And what issues does that mean? It means you can't add to the middle or front of a queue. You can only add to the rear. So, thank you for watching, everyone. Hopefully this cleared up queues and stacks for you, and it made it a bit easier to understand what's going on.